Hi everyone. In today's talk, I'm going to be moving on from a previous video which I did on the surface-to-surface radiation model, and I'm now going to be looking at the discrete ordinates radiation model. This model is a bit more involved than the surface-to-surface model that we looked at previously, and we have to start thinking about beam directions, and there are another few difficulties in this model that we may not have come across before. So we've got a scattering integral term to think about, and we also need to think about how we can speed up the solution process, because we end up having to solve a lot of additional equations to solve the discrete ordinates radiation model. So this is a bit of a different radiation model to what you might have seen before. If you've come across it before, it might appear a bit confusing at first glance. So in this talk, I've really tried to simplify everything out down to the first principle, so you should get a great understanding of what the discrete ordinates model is actually doing under the surface. So sit back, take some notes. I know you're going to find this talk extremely useful. So starting off with the background for this video, in a previous video I went through the surface-to-surface or S2S model for radiation, and this model is useful for us when we have some hot surfaces and they're surrounded by a gas medium that doesn't participate in radiation, like a vacuum, for example. In that case, the surface-to-surface radiation is very useful for us, and it's very easy for us to set up and use. However, if the gas that's in the medium does participate in radiation, then we can't use the surface-to-surface model, and we need to account for the gas in the medium in some way. And the discrete ordinates model, which I'm going to be talking about today, is one example of a model we can use when the gas in our medium does participate in radiation. So what do we mean by participates in radiation? Well, more specifically, the gas will absorb and scatter some degree of radiation that's passing through the medium between the hot surfaces. And just to give some examples, CO2, water vapor, and soot all participate in radiation. So when we tend to have applications with combustion and exhaust gases, for example, the gases in those scenarios do participate significantly in radiation. And so we need a model that we can use to account for that participation between the surfaces. And compounds like hydrogen, nitrogen, and oxygen don't participate significantly in radiation. So clearly, when we're choosing our radiation model, we need to use some judgment as to what degree we think the gaseous medium will be participating in the radiation, and then selecting a model appropriately. But for today's talk, I'm only going to be focusing on the discrete ordinates model. And you could actually use the discrete ordinates model whether the gas participates in radiation or not. So that's all I'm going to say about the selection of models. Let's move on to the model itself. Now, the first thing we need to think about before we can actually look at the discrete ordinates model itself is actually look at the radiative transport equation, or RTE, as you'll sometimes see it abbreviated in the literature and in user guides. And in order to understand the radiative transport equation, we need to think about radiation intensity, because this is the variable that we'll be solving for in the radiative transport equation. And radiation intensity is often given the symbol I to denote intensity. And the important things to remember with this variable that make it different to other variables that we're used to solving for is that the radiation intensity is a function of spatial coordinate r. So at a position in space in the gaseous medium, the radiation intensity will take a given value, so it's a function of r. But the radiation intensity is also a function of the beam direction. And the reason that the radiation intensity is a function of the beam direction is because radiation travels in straight lines. And so what we'll see in the radiative transport equation is this variable I is written as a function of r and s. Now, this is different to variables that we're used to seeing in computational fluid dynamics, like temperature and velocity, for example, where these variables are only a function of the position in space. So they're only a function of r, and they're not a function of some beam direction. So we're going to bear this in mind when we look at the radiative transport equation, and then show also how we can deal with the radiation intensity, because it's also a function of the beam direction. So equation 1, which you can see there, is the radiative transport equation. And it's quite a long and complicated equation, as you can see, with lots of different terms and different variables in there. So don't worry if this seems overwhelming at first. In this talk, I'm going to be going through each of the main variables in the equation so that you have a good understanding of what the equation is doing, at least at a surface level. And what I want to do on this slide is just start by looking at the notation used for some of the terms and the constants in the equation, so that you at least understand what those are before we dig in a bit further. So sigma is the Stefan-Boltzmann constant, which is 5.67 times 10 to the minus 8. That's fairly commonplace. And we've also got sigma sub s, and the sub s there is to make sure that we distinguish sigma s from the Stefan-Boltzmann constant. And the sigma s is the scattering coefficient of the gas, so how much the gas scatters radiation intensity. A is the absorption coefficient of the gas, how much radiation does the gas absorb, and n is the refractive index of the gas. Then, as I noted before, r is just the Cartesian coordinate in space, so x, y, z, as we're used to, and s is the unit vector in the direction of the beam. So if you think of a normal vector with components nx, ny, and nz in the direction of the beam, that's what r and s are. So really, when you look at this equation, the variables r and s, which you'll see in brackets after I there, they're just telling us what things that the radiation intensity is a function of. So you could probably just cross those brackets out if it would help you, and it helps simplify the equation a bit so you don't notice all the terms in there. It makes it easier for you to understand. But what I want to draw your attention to on this slide is that the terms I've highlighted in red there, that's sigma s, a, and n, these are material properties of the gas. And as with any CFD simulation, we always have to define material properties of our fluid or our gas before we solve the equations. So this is similar in a way to the dynamic viscosity, the thermal conductivity, the density, and the specific heat capacity. These three additional variables are new material properties that we need to define for our fluid before we can carry out the simulation. And we're used to dealing with material properties in CFD, so that is not a problem. Now, a couple of things you'll also notice about the radiative transport equation is that there's no velocity field in there. And the reason for that, of course, is that radiation is not transmitted by the velocity field. So we're not thinking about convection or conduction here through the fluid. Radiation is transported by electromagnetic waves, regardless of the medium. So there's no velocity field in there at all. And the other thing to notice is that we have an integral term on the right-hand side of the radiative transport equation. And we may not have seen integrals appearing in our transport equations before, so this is fairly unusual, and we're going to have to think quite carefully about how we deal with the integral if we want to come up with a solution for this radiative transport equation. And what I'm going to do now is just group all of these terms together so that you really understand what each of the parts of the equation mean. So the first collection of terms there is just the rate of change of intensity through space. So as we move through space, we expect the radiation intensity to change. As we get further away from a hot surface, for example, we expect the radiative intensity to reduce. So that first term allows the radiation to change in space. The second term there represents the absorption of radiation intensity by the gaseous medium. Then on the right hand side we have an emission term. So remember now that our gas itself might be hot, and when the gas is hot it's also going to emit radiation, and that term there accounts for the emission of radiation by the gas. And then the final term on the right hand side represents the scattering. So what the gas will tend to do is it will scatter radiation and change its direction from one direction to another. So you can think of this integral term as deflecting a beam. So if there's a straight beam of radiation traveling in one direction, the scattering term is going to change the direction of that beam into another direction. And I've just made a small note on this slide that the reason this equation is challenging to solve with CFD codes is for two reasons. Firstly, we have this integral term on the right-hand side, and secondly, we've also got a direction variable s. And these two things are things we're not used to seeing in typical CFD equations that we might solve, but I'm going to go through those briefly in the slide here, which show you how we solve them. Now, the discrete ordinates method, which I'm going to focus on today, is one example of a method that we can use to solve the radiative transport equation. There are other methods we could use, but specifically in this talk, I'm only going to talk about the discrete ordinates method as one example of a method we can use. So how does the discrete ordinates method work? Well, the trick with the discrete ordinates method is, rather than think of the infinite number of directions that a beam could take, so if you look at the picture there on the left hand side, you can see that if we're at a point in space, radiation could be incident on that point from any number of angles. So an infinite number of discrete angles could be incident on that one point. And the trick with the discrete ordinates method is, rather than solve for an infinite number of beam directions, we're only going to solve for a discrete number of beam directions. And the picture which you can see there on the right, I've chosen to show 8 beam directions only, and we assume that the radiation intensity is constant over that beam angle, which you can see there, which is given by delta omega. So this is really the trick with the discrete ordinates method, is rather than having an infinite number of beams, we're only going to have a finite or discrete number of beam directions. Now, just a small note on notation for those of you who use ANSYS Fluent. ANSYS Fluent chooses to discretize these beam directions using octants. So if you look at the image on the left hand side there on the slide, you can see that 360 degrees is split into 8 octants. So an octant is an eighth of 360 degrees. And ANSYS Fluent allows you to specify the number of segments that each octant will be divided into. So if you look at the second image there, when you set n theta, that's a parameter in ANSYS Fluent, you're selecting the number of segments that you divide each octant into. So you can see that actually the total number of beam directions that we'd be solving for would be 8 multiplied by the number of segments n theta there. So I really wanted to make this point because it's quite easy to think otherwise that, for example, ANSYS Fluent would only be dividing the full 360 degrees into n theta segments, but actually by default we've already divided the 360 degrees into 8 octants, and we're going to specify n theta segments for each of those octants. And the final thing to note here is that ANSYS Fluent also uses the symmetry property. So rather than solving for 8 n theta segments in total, we're only going to solve for 4. We only need to solve for half of them because of the symmetry plane there. And of course, the octants which I've shown here on the slide are in 2D, but exactly the same principle applies in 3D, where, as well as introducing n theta, that will be the number of segments per octant in this direction, we also introduce n phi, which will then be the number of divisions in that third direction. So from this slide, what you can see here is that when we're discretizing that radiative transport equation into a finite number of directions, they're going to be a minimum of 4 directions solved in 2D because of the symmetry plane, and a minimum of 8 directions solved in 3D. And that would be the case if you decided to set n theta and n phi equal to 1. However, in general, we may choose to solve for more directions than this. Now, the main thing to understand with the discrete ordinates method is that we're going to be solving one transport equation for every beam direction S. So on the previous slide, if we had 8 octants and we had kept each of those octants as one segment, then we'd be solving 8 additional transport equations. And just on the slide here, I've just wanted to really spell this out for you so you can see that we're going to be solving that radiative transport equation 8 times if we have 8 directions. And if you look carefully at the left-hand side here, you'll see that we've got I1 and S1, and we've got I2 and S2, and so on for each of the equations. And that's because we're solving a transport equation for each beam direction. So we'd have direction 1, that would be S1, direction 2, that would be S2, direction 3, that would be S3, and so on as we move around the circle. So this is the key thing to think about with the discrete ordinates method, is that even though we've only got one radiative transport equation, we're going to be solving it multiple times for each of the directions that we're considering. And the way I like to think of this is that for every cell in the mesh, we're going to be calculating a beam intensity in each direction. So I've just given you some examples here. We've got I1, that would be the beam direction going diagonally down to the right. We've got I2, the beam direction going to the right, and then I3, the beam direction going down, and so on. So at each cell in the mesh, we'll be calculating a radiation intensity, that'll be an I, but a radiation intensity in each direction. So I find it helps to think of I1, I2, and I3, etc. as different variables. And we're going to be calculating each of those variables using an additional transport equation. So now what I'm going to do, now that we've thought about the radiative transport equation, and actually we're going to solve it by solving the equation multiple times in multiple directions, we're actually going to have a look at what each of the terms in the equation actually mean and how they affect the solution. And I've just highlighted the terms for you there. We've got the rate of change term, the absorption term, emission term, and the scattering term. And what I'm going to do is go through each of those terms one by one now to help you out. So starting with the first term, the rate of change of radiation intensity. And to help you understand this term, if you think of the nabla.is, which is the term we're looking at there in equation 8, you can actually expand this out and collect the terms together. And what you'll find is that this expression actually evaluates to partial I by partial S, which you can see there in equation 9. And this is explicitly telling us it's the rate of change of intensity in the direction of the beam S. Because remember that the beam isn't necessarily aligned with the X, Y, or Z axis. It's probably going to be at some angle to that, depending on how we discretize the octants, which we saw earlier. So why is the rate of change of intensity term important? Why do we need that? Well, we need the rate of change of intensity to allow the radiation to vary between the cells in the mesh and to vary across the mesh. And if we didn't have this term in the equation, so if you look at equation 10, if we set that first term to 0, then what that will be telling us is that at every cell in the mesh, the total radiation intensity remains constant, and we would just have a balance between absorption, emission, and scattering. And that situation would result in the picture, which you can see there at the bottom of the slide. Looking at every cell in the mesh, the total radiation intensity would just be the same. And clearly this is not physical. We need the radiation intensity to vary, because as we move away from the hot surfaces, we expect the radiation intensity to reduce. So this is why we need that rate of change of intensity term, which we can see on the left-hand side. The second term to look at is the absorption and scattering terms. And you can see there we've got the coefficients A and sigma S in there, multiplied by the radiation intensity. And these terms actually act to reduce the radiation intensity. And the reason they do that is if you think of moving that term to the right-hand side of the equation, we get equation 13. And you can clearly see here that this is actually a source term, but it's a negative source term because of the minus sign there. Remember in CFD equations that if you collect all the terms on the right-hand side that don't involve derivatives, these are all going to be source terms, and the sign of the source term, positive or negative, tells you whether it's a source or a sink. And for the absorption and scattering, we've got a negative sign there. So this term acts to reduce the radiation intensity. And if you look at the small diagram which I've got for you there, if you move along the beam direction, so from left to right, you can see that the beam intensity in this case is reducing. And that's because the radiation is being absorbed and scattered by the gas in those cells as we move along. And that's a physical effect that we need to account for, and it's the reason we have it in the radiative transport equation. So what about the emission term? Now this is also a source term on the right hand side of the equation, but this time you can see that it's positive, And because the emission term is positive, that's a positive source term, and we're going to be generating radiation. And the reason we do that is because the gases are generally hot, and the hotter the gas is, the more it will emit radiation. So if you look at the example picture there, which you can see on the slide, moving along the beam direction from left to right, you can see that because the gas is hot, it's emitting radiation, and the radiation intensity is actually increasing in this case. So we've just looked at two terms there. We've got an absorption and scattering term, and we've got an emission term, and this will allow the radiation to either increase or decrease as we move through the medium, which is what we physically expect. And now for the final term in the radiative transport equation, we've got the scattering integral. And this is by far the most complicated and confusing term, which is why I'm going to take it nice and slowly for you, and hopefully by the end you should have a good idea of what this term actually does. So the integral there, the reason we have an integral is that is an integral over all of the beam directions. So at the start, when we looked at the radiative transport equation, remember that we have an infinite number of beam directions coming into a point. And so we would have to, if we wanted to know how radiation was scattered, we would have to integrate over all of those beam directions to tell us how the radiation intensity changes between directions. But remember that we're now using the discrete ordinates model, and in the discrete ordinates model we only have a finite number of beam directions, and for the example picture I showed you we had 8 beam directions. So what that means is we can replace the integral over all of the directions with a summation over the number of beam directions that we chose to solve for. So that allows us to go from equation 15 to equation 16. And you can see here what we've got is we've got a summation over the number of beam directions, and for each of those we've got an intensity, and then phi j, which you see there, is a scattering term, which tells us how much of the radiation in another direction is scattered into the direction that we're looking at. And then multiplied by delta omega, of course, because that's the angle between the beam directions that we're solving for. So we need that to get the correct summation there over all of the angles. So just to help you think about this a little more, and the way I think of the scattering term is, if you think of an incoming beam there, I2, then that incoming beam will be scattered into the direction I1. So we'll be going from direction I2 into I1 over an angle delta omega. And the degree of scattering, or how much the intensity changes as it is scattered, is controlled by this function phi, the scattering term. And in this talk I'm not actually going to go into the scattering function and details of how it works, because it's a bit confusing, but for now I think it's just important to appreciate that that term phi controls what degree of radiation intensity is scattered from a given direction into the direction we're interested in. And the summation, of course, is required because we need to work out, of all of the beam directions that we have, how much of the intensity from those directions is scattered into the direction we're currently solving. So if we were currently solving the radiative transport equation for direction 1, say left to right on the page, as I've got for you there, the red arrow, then we would be doing a transport equation in the direction from left to right across the page for the radiation intensity I1. And when we get to the scattering term, we want to know what degree of all of the other directions is scattered into the direction I1 that we care about. And so if we were to expand out that summation term, you can see there in equation 18, we've actually got a source term with an I1 phi 1, I2 phi 2, I3 phi 3, etc. And what that is it's telling us for all of the other beam directions what degree of those intensities is scattered into the direction we're currently looking at. And this is why we have a source term for every other beam direction, because all other beam directions could be scattered into the direction that we're currently looking at. And the degree of scattering is controlled by that function phi, which we're not going to look at. So hopefully now you've got a bit of a better understanding about how, why that scattering integral is needed, how we convert it into a summation, and then what the summation actually means. And the summation is just a set of additional source terms for scattering. So what you may have noticed up until now is that with the discrete ordinates radiation model, we have to solve a lot of extra equations. So if we had 8 beam directions, we'd have to solve 8 additional transport equations. And in CFD, we're already solving a lot of equations. We have to solve the 3 momentum equations, an equation for pressure, and then we often have to solve 2 additional equations for turbulent scalar variables, for example. We've then got the energy equation. So we're already solving a lot of equations. And if we have to solve an extra 4 or an extra 8 equations for radiation, clearly this is going to slow down the solution process quite significantly. And so the way that CFD codes typically get around this with the discrete ordinates radiation model is only solving the radiation model every 10 iterations of the flow equations, for example. And the reason we can do this is because the coupling between the flow equations and radiation is very weak. So the only variable that really comes into the radiation equations is the temperature of the fluid. There's no velocity or pressure terms, for example. And so what that means is that the radiation field is actually going to change very slowly and only really in proportion with how the temperature field changes. So what you'll find often in CFD codes is that there'll be an option of how many iterations of the flow field you want to solve before solving the radiative set of equations, and typically we solve it every 10, and that ends up being a good compromise and allowing us to get to a solution a lot more rapidly than if we solve the radiation equations every time step. So the final thing I want to do is just speak briefly about the coupling between the radiation equations and the energy equation, so for the actual temperature field in the gas. And the way that this coupling is achieved is at the boundaries of the domain. So you'll notice, of course, if you turn on radiation models and you solve a flow field with hot surfaces with radiation on, then the temperature of the walls will increase relative to the local fluid. But the fluid itself, its temperature isn't really affected by the radiation model being on. It's only the boundary surfaces that heat up due to radiation. And what we do, and the way that we couple radiation with the energy equation, is at the boundary faces. And what I've got for you here is a small diagram just to show you a cell which happens to be adjacent to a boundary. And what you can see is that the wall at the bottom, in this case, we're going to treat as opaque, meaning the radiation doesn't pass through it, it's just going to be absorbed and heat up the surface. Now, there are other types of walls. You can have semi-transparent walls and translucent walls, but these tend to be a bit more difficult to deal with. And to keep this talk nice and short, I'm only going to talk about opaque walls because they're going to be the majority of engineering surfaces that you encounter. And so on this wall, we're going to have radiation intensity incident on it from a number of different angles. So if we had 8 beam equations, we would have 8 different directions of radiation intensity incident on the boundary surface. And the total heat flux per unit area incident on that face is going to, of course, be the integral of each of these beam intensities, but we need to take the dot product of the beam and the unit normal vector to get the component that's actually normal to the surface. That's why you see the dot product in there. And of course, because we're using the discrete ordinates model, that summation, that integral now just becomes a summation over all of the directions, and all we're really doing is just taking the dot product there with the unit normal vector and adding them up, and that will give us the total heat flux into the face due to radiation. So when we think of the energy equation and what we'll be doing and how it will be solved, remember that for each cell in the mesh, we're going to be having the heat fluxes across each of the faces into the cell, and that makes up the energy balance. Now, when we add radiation in for that wall face, which we can see there, we're now just going to have an additional flux of heat into the cell from that face, which will add to the flux of heat from the wall boundary temperature and any other fluxes which we may have from the equations there. So really straightforward how the radiation intensity is coupled with the energy equation, but it's important to remember that this only happens on the boundary face adjacent to the walls. So just a summary now to wrap up the talk. The discrete ordinates method is one method of solving the radiative transport equation. There are other models, I just haven't chosen to go through them today. And the discrete ordinates method is useful for us when the gas participates in radiation through absorption, emission, and scattering, for example. And so in order to carry out this analysis and make the decision of what radiation model we want to use, we need to know 3 additional material properties for the gas. And that'll be the scattering coefficient, the absorption coefficient, and its refractive index. So once we know these coefficients and to what degree the gas participates in radiation, we can set up the discrete ordinates model and solve if we want. And then the final thing to note, of course, is that what the discrete ordinates model is doing is solving an additional transport equation for every beam direction that we decide to solve for. And we're going to solve for a minimum of 8 octants. That'll be 8 directions in 2D and a similar extension in 3D. So that brings me to the end of the talk. I found this talk particularly difficult and particularly challenging to put together because there wasn't a lot of information out there on the discrete ordinates radiation model. And it took me a little while to try and work out exactly what was going on, how it was working, and how we deal with the integral scattering term, for example, and the beam directions. So quite a challenging talk to get your head around, but hopefully after watching this video, you've really started to understand the basics and the principles of the discrete ordinates radiation model and how it works. So let me know how you found it. Did you enjoy the talk? Let me know in the comments section below, and if you have any more thoughts, I look forward to hearing from you.